Right. Welcome everyone. So we are delighted today to have Tengyu Ma from Princeton University. So Tengyu is a student of Sanjeev Arora and he's going to tell us about non-convex optimization.
Okay. Thanks for having me here, and thanks for coming. So I changed my title and the content a little bit. So I'm still going to talk about matrix completion as promised, but in the last 10 or 15 minutes, I'll mention some recent work with Maurice Hart on linear residual networks, which I'm quite excited about. So the matrix completion one is joint work with Rongo and Jason Lee from Duke and USC, and the last one, the linear residual network one, is with Maurice Hart. I'm Tengyu Ma from Princeton. So I'm going to talk about non-convex optimization. So just to put this talk into a little bit broader context. So let's start by comparing convex optimization with non-convex optimization for machine learning problem. So on the convex side, we have a beautiful theory about convex functions. We have fast algorithms for pretty much all of the situations, like smooth, non-smooth, strongly convex, non-strongly convex, a sum of convex functions. And these algorithms are fast in practice and in theory. So on the other side, non-convex optimization in the worst case is NP hard. So it sounds like we don't even have a comparison here, right? So on one side we have everything, and on the other side we have nothing. So, but sometimes you have to think about it and ask the question: what if you really want to optimize a non-convex function, right? So in terms of machine learning, this means that corresponds to what. If you want to optimize, you want to learn some complex models beyond, linear models. Like, if you want to do neural network with empirical risk minimization, or if you want to maximize log likelihood for, many generative models, like, for example, mixture of Gaussians. So, the kind of the recipe that the convex world offers us is the idea of linearization. So linearization could mean probably two things. One is the kernel machine, right? So you lift your feature, your input, into a higher dimension, and in the new space you learn a linear classifier. So that's one way to linearize your model, and the other one is that you can do convex relaxation, which linearize your variables. So you introduce the auxiliary variables, and to make it linear, and there's a generic way to do all these convex relaxations, like sum of squares relaxation these days. I love this posted method. Actually, I worked on some of the convex relaxation things. But however, it seems that we have to admit that these are not efficient enough. Right? Often you can get polynomial dependency on either number of examples or the dimension. But these days you have a million examples, and the number of parameters is something like probably 10 million. As long as you get something like n squared, d squared, if n is example number of examples, it's going to be a disaster. So it seems that they are not efficient enough. On the other side, there's a very simple way to do non-convex optimization in practice. You just do stochastic gradient descent. So these are very scalable, very easy to implement. These days we have all this auto differentiation package like TensorFlow. I apologize, I still use TensorFlow in my talk. Maybe I should choose something from Microsoft. But anyway, so you don't even have to write down your compute your gradient by yourself. You just need to write down your model, and with another 2 lines of code, you take the gradient and do whatever optimizer you want. So, all right. So everything is perfect here except the elect theory. So it works, and it works perfectly well. It is the main algorithmic technique behind all of these breakthroughs in NLP, in computer vision, like speech recognition. So, but we don't really know too much about the theory behind it. So the question that I'm asking in general here is that can we understand non-convex optimization better and improve it? So I mentioned that it is simply hard to optimize non-convex functions in the worst case. However, the hope here is that for structured learning objective functions on real-life data, it's very likely that these problems are not NP hard, and we have a strong empirical evidence for that.
So one question: so is there a notion of like approximations for non-convex in the way we deal with NP hardness in combinatorial optimization?
I guess you can, but it's not clear whether those approximation guarantees can lead to anything for machine learning problem. Maybe sometimes it can, but but you have to argue about that. Like, it's not like the optimization is not the only goal, especially for machine learning. So and also the way to phrase approximation also probably is different, right? Probably multiplicative approximation may not mean anything. You maybe need additive approximation, so on and so forth. Okay, so let me have a list of problems that can be solved by non-convex machine in machine learning. This is just a partial list. I try to sort these problems according to the difficulty of the analysis, and my criteria is my very biased opinion is my criteria is the lack of linear algebraic structures. Of course, also difficult analysis doesn't really mean everything. So, but let me just list it according to this criteria. So kind of the ultimate goal, probably in the short term, at least, is to understand how to train neural network or other variants like a recurrent network, long short-term memory. So, and these are problems that we don't know how to do in theory, but empirically we can do it very well. So, in terms of theory, what we could analyze and understand these problems. So, I guess for SVD and PCA, these are folklore, and the only way to do it is using non-convex methods. I guess this line of research really starts with the generalized linear model by the study by Kallai et al. And also Hazen et al. Has some other study about it. So, and also recently we know that if you do SDP, you can, for example, if you have a small number of constraints in your SDP and you know that the optimal solution is of low rank, so you can try to use the low rank parametrization and do gradient descent for the SDP. And we know that for generic SDP, this can be solved in polynomial time. And also there are works on linear deep neural networks and linear residual networks, which I'm going to touch on a little bit at the end of the talk. And for matrix completion, this is the main subject of this talk. And Gaussian mixture model. For linear recurrent network, this is the joint work with Maurice Hart and Ben Recht. So the kind of the difficulty is that you have to apply some linear transformation again and again. So you have a power of some matrix, which is not exactly within the scope of a linear algebra. So you have to do something special for it. And finally, tensor decomposition is one of the problems I think is closest to neural network from a technical point of view, because for all of the problems except tensor decomposition that we can understand, there are some rotational invariance in it. And for tensor decomposition and neural network, they share the property that there's no rotational invariance, but there is a permutation invariance. By permutation invariance, I just mean that, for example, if you take your neural network and you permute the nodes in one of the hidden layers, and the network remains exactly the same in terms of the input-output relationship. And this is true for tensor decomposition. However, you cannot rotate some weight matrix and rotate it back in the next level if you have nonlinearity. Okay, so this is just a general overview, and I'm going to talk about matrix completion and linear ResNet in this talk. So I often got asked the question whether there's any unified theory behind all of this non-convex optimization. So I guess the short answer is, unfortunately, or maybe fortunately, for the in terms of the research, we don't have anything yet. However, they are kind of candidates. So the candidates is that there is a general kind of conjecture that maybe this non-convex optimizations in practice is easy because the objective function has very nice geometric properties. So for example, one property that we know suffices is that all local minima are global minima. So if this is true for your objective function, then it can be optimized in polynomial time, because gradient descent or some other local search algorithm can converge to local minima in polynomial time under some very mild regularity conditions. So this is the kind of the common property of an analysis in these problems: SVD, SDP, linear neural network, matrix completion, so on and so forth. So this is a plot of a function with this property in 2 dimensions. So you see that they are 4 global minima here with error 0, but actually they are saddle points like here, here, and also there's a saddle point around the peak. So but there are no any other bad local minima. Okay, so another property, a stronger property, strictly stronger property, is that all critical points are global minima. So, by local minima, I mean that the gradient is 0 and the Hessian is positive semi-definite, and the critical points just means that the gradient is 0. So if all critical points are global minima, then we also know that you can converge to the critical points in polynomial time, and actually we have a fast algorithm to do that. And this is the geometric property behind these problems. Gaussian generalized as linear model, linear recurrent network, linear ResNet. So this is another example of functions with this property. And you can see that the only place with gradient 0 is this kind of line, and this line consists of all of those global minima.
Can you explain what you mean by ResNet?
Yeah, I'm going to define it. Yeah.
Okay. Because this talk is also hosted on ResNet.
Oh, yeah.
So people get confused.
This is a residual network.
Is it the one that proposed 1 year ago in computer vision? So, okay,
Yes,
I know.
yeah, by the He and et al. In my
I was just
on my
wondering
side.
if there's another definition in
No, it is exactly.
And also, like any of these problems NP complete.
In worst case, sure. If how do you say a problem is NP complete? You write down some objective function and you say, okay, optimizing this function is NP complete. Yes, I think maybe all of them. Yeah, it should. Oh no, not for the linear ResNet. No, not for the linear case. Let's see. Yeah, maybe not this linear neural and linear ResNet, because these are not real machine learning problems. These are more or less test problem for understanding optimization landscape. I'll cover that in a moment. Any other questions? Okay, so however, so these properties are good, and we know that under if the function have this property, then we can optimize it efficiently. However, the difficulty is often not about the optimizer. It's really about how do you verify the object function has these geometric properties. So just to this is not the same as this doesn't happen in complex world, but in the convex world, because usually if you want to verify your function is convex, you just say, okay, maybe your function is a sum of convex functions, and each of term is convex, then the sum is convex. So, however, these kind of properties are not even preserved under addition in general. And sometimes the reversing happens. For example, you have a sum of things, and each of them doesn't have this property, and you take the sum, and you start to have these kind of properties. So, so we don't have very good, ways to verify these geometric properties. That's kind of like a technical goal of this line of research is to develop more mathematical tools for characterizing the landscape of these non-convex functions. All right, so this is the general big picture, and let me talk about matrix completion next. So the definition of matrix completion is simple. So we have a low-rank matrix M. We only observe a random subset omega of the entries of M, and our goal is to recover all of the entries of M. So the typical application of this problem is, recommender system. So the typical scenario is that, you have this user item preference matrix, and each entry is the, the rating of user I to item j, and you only observe, a small fraction of this matrix because not every user rates every item online. And the goal is to recover all of the entries so that you can recommend the items to the users. Okay, so concretely, we are going to focus in the subcase of matrix completion in this talk. So the symmetric version, where we assume M is of rank R, and it's symmetric and positive semi-definite. So this translates to that M is of the form that M is equals to Z times Z transpose. Here Z is a tall matrix of dimension D times R. D is the ambient dimension, R is the inner rank. So and we assume that each entry is selected into omega, the set of observations, with probability P independently.
You use different, like Z and Y. Here you use the same one?
Yeah, so this is that's why this matrix is a special case.
Okay.
Yes. So so we are going to do non-convex maximization, and our variable is this low rank factor x, which is of the same dimension as z, and ideally we want x to be z. And the loss function that we analyze is the following, right? So basically it's the sum of the errors on every observed entry. So here XX transpose is the matrix that we predict, and XX transpose sub ij is the ij's entry, and we take the difference between the prediction that we have and the real value, and we take the sum of squares of the error over the observed entries. So it turns out that it's useful to define this notation up front, just to simplify some of the notation. So let's define P omega of A as the restriction of A to the subset omega. By this, I just mean that, we have this matrix A and the blue entries are in omega, and P omega of A is just, you zero out all of the entries outside the omega, and you keep all of the blue entries inside omega. So using this notation, we can rewrite a little bit succinctly, this objective function as P omega of M minus P omega of X transpose for binom square. So for binom is just the sum of squares of the matrix. So we can have this. Okay, so this is our objective function that we're going to analyze, and here is our main theorem. So under the usual assumptions, all local minima of this function f are global minima, and they all recover the underlying matrix M. So just to define the terminology here, so local minima means points with vanishing gradient and a positive semi-definite Hessian. This in particular implies that stochastic gradient descent finds a global minimum with arbitrary initialization in polynomial time, because stochastic gradient descent can find the local minimum, and here all local minima are global minimum, therefore stochastic gradient descent can also find global minimum. Okay, so just to clarify what do I mean by usual assumptions, I mean M is incoherent, while conditioned, and the sample complexity, right, the expected number of observations that we need should be larger than d times r to the 6. So basically, for each row you have r to the 6 observations. The optimal sample complexity is d times r, and so we lose polynomial factor on r compared to the optimal sample complexity. But we didn't really try very hard, and the main priority is to get the factor d correctly. So I won't define incoherence and well condition in this talk, because they won't appear another time in this talk. So I'm trying to sweep it under the rug.
Seems to be a deterministic statement.
Oh yeah. So I should say with high probability over the choice of omega, this is true. Yeah.
And how sensitive is this to noise?
So we can also prove a noisy noise version. So if you don't observe the exact entries of M, but you observe M plus some noise, it's also fine. So but you don't get exact. So here you get exact recovery of M, and if you have noise, you don't get that. Any other questions? So I also cheated a little bit about the objective function that we are finally going to analyze. So in fact, we are going to add a regularizer that enforces incoherence, although I haven't defined incoherence for you. But this is not important for this talk, for the purpose of this talk. So and there are other properties that probably help to build up the intuition. So f is not convex, first of all. And also there exist critical points that are not global minima. And also another property that is useful is that all global minima have the form that x is equals to z times r. Recall that z is the ground truth factor. And so basically if you rotate the ground truth by any orthogonal matrix, it will remain a global minima. Okay, so
how tight is this d times r6 power? The r to the 6th power.
Mm-hmm. How
tight?
Oh, yeah. So the optimal complexity that we know, if you use convex relaxation, this is d times r, without the power 6. And we to be honest, we didn't try very hard to reduce this power. So I think if you just use our thing with a little bit tightened